Happy Thursday. Continuing with integration. Need to evaluate using the limit definition. Delta x b minus a over n. Our function is 3x minus 1. It does not matter how we set up the Riemann sum. So you take the limit, it's going to converge to the same thing. So we might as well just use a right endpoint. Was that right? There's a problem with that. What's x sub I? No comment. X sub I is the right endpoint, right? These windows suck. Either that or they're extremely loud. We need a formula for it. Well, right endpoint of the first interval would be A, right, your starting point, plus delta x, wouldn't it? Right, plus the length of the interval. Second right endpoint would be the left endpoint plus delta x. But the left endpoint is the right endpoint of the previous. So isn't that now a plus 2 times delta x? Third interval, right endpoint. Right, it's the left endpoint plus delta x. Using a similar argument, that winds up being a plus 3 delta x. So in general, the ith right endpoint would be a plus I times delta x. Perfect. Delta x is 4 over n. A is -1. Right? I times 4 over n. But f of x is 3x minus 1. So evaluate f of x at the -1 plus 4 over n I. Simplify, you should get -4 plus 12 over n times I. Now use properties of summation. Specifically use the linearity properties. Sum -4 from I equals 1 to n. Just -4 times n, isn't it? That was one of the properties. Summation I equals 1 to n of I. It's one of those special sums. N times n plus 1 all over 2. Distribute that 4 over n through. Not 6, 24. Got that 4 over. Got that 4. That's the formula for R sub n. So our integral is the limit of that as n goes to infinity. What's the limit of negative 16? What's the limit of 24n times n plus 1 all over n squared? The integral's 8. Yay, we've done our first Riemann sum limit. That's nice. Function's not linear now. But the process will be the same. What's delta x? Three over what? You said it was n?
Yeah.
3 over n. Function is 2x squared minus 3. So terminology, this piece here, the function that we're integrating, is called the integrand. So if you hear me refer to the integrand, that's what I'm referring to. Again, it does not matter whether we use left endpoint, right endpoint, midpoint. So we might as well use the right endpoint. Delta x times the summation, I equals 1 to n, f of a plus I delta x. Bummer. We have to expand out a squared. So it's going to be 1 squared times 2 minus 3. There it is. Okay. And so then twice the product, which would be 6 over ni, then times 2. Nine over n squared times I squared, you square the second term, times 2. There's what we're taking the sum of. Use your linearity properties. What is that first sum? What is that second sum? Come on, you said you've done Riemann sums before.
We did sigma. We did everything like without sigma. We did the definition of sigma. Oh.
Didn't know there's a way to do Riemann sums without summation notation.
No, I don't remember. Algebra.
Summation of I we just did it. Summation of n of I squared. I equals 1 to n. Again, one of those special sums that was given. N times n plus 1 times 2n plus 1 all over 6. -3 plus (18) n times n plus 1 over n squared plus 9 n plus 1 2n plus 1 all over n cubed. So again, there is our Riemann sum. Our integral is the limit of the Riemann sum. It's the limit of the first term. Second term. Third term. So the integral's 33. What's delta x? Integrand. X cubed minus x squared. This wasn't too bad. 1 over n times summation I equals 1 to n. F of a, which is what? What's a? What is it? 0. Oh, that's nice. Plus I delta x. Evaluate f of x at 1 over n times I. Linearity properties. What's the sum of I cubed? What about the sum of I squared? There's our Riemann sum. Sake of space, I'm just going to write this for the limit. What's the limit of that first term? And limit of the second term, which is what? Negative 112. So you just ignore it. Riemann sums aren't that bad. Riemann sums are fine. Just requires a lot of algebra. Of course, we only went up to x cubed. Whatever's like x to the 8th. What was an 8th degree polynomial? True. But what's the summation of I to the 8th? From I equals 1 to n. Or I to the 7th, I to the 6th. Well, let's really make it interesting. What about e to the x? Or natural log of x? Or cosine of x? Now the Riemann sums start to get really hairy.
This is what I was doing.
That's what we're doing.
Yeah, but this one was what we wrote down something.
It's literally the exact same thing.
This one does not have sigma in it.
Now we're going to worry about those instances later. So let's integrate the square root of 4 minus the quantity of x minus 2 squared. What kind of shape is that? If you have to graph this, that makes me very sad.
Sorry, I'm very sad. Emotions are not good. Keep it.
What's that curve? Oh dear. What kind of circle? Be more specific. What's the radius? Where's it centered? Yeah, but you cheated. You looked at a graph. That is the upper semicircle of the circle radius 2 centered at 2, 0. What's the radius? What is the area of a circle? The circumference. Area. Pi r squared. So the area of this circle would be 4 pi. What was the integral? Assigned area. The upper semicircle lies above the x-axis. It's going to be a positive area. So if you look at the integral from 0 to 2 of f of x, isn't that half of the semicircle? What's the area of the semicircle? That's the circle. So what's the area of the semicircle? What is it? Half of that. It's just pi. Well, what about that integral? It's also just pi. It's half of the semicircle. What about that integral? That's the whole semicircle. That area is 2 pi. By the way, if you didn't use geometry, that's a Calc 2 integral. We won't be able to evaluate that analytically in this course, but we can using geometry. So this one I am going to have to plot. What's that integral? It's 4. That's nice. This region is also supposed to be shaded. But for some reason, the shading isn't coming through the projector. What about that one? Since this projector doesn't want to show that shading, just draw the shapes. Because that's not light shading either. That's very dark shading. You can not believe me all you want. Just wait till the slides go up on Canvas and you can see for yourself. If that's the case, then I just believe that you got a 0 in this course. So what is that area? What is that integral? 1 to 2. I know where you're getting -8 from. That is not the intention. That 4 applies to the whole thing, not just the half. -4. Why is it negative? That would be -2. They didn't ask this, but I'm going to ask it. What's that? It's 4. So using the limit definition is kind of a pain. Using geometry has its own drawbacks. Right. For instance, those are not triangles. So finding the area of those, not fun. I think you can do it with geometry. It's just not fun. So we want a way to evaluate an integral that doesn't require the limit. That's what we're going to work towards. It's called the fundamental theorem of calculus. But before we can apply the fundamental theorem of calculus, we need another term. So the derivative, remember, it had a function, right, that we could evaluate called the derivative function. Is there an equivalent function for integrals? The answer is yes. It's called the antiderivative. A function, capital F, is an antiderivative of the function f if capital F prime of x equals f of x for all values of x in the domain of f. Derivatives were unique, right? Each function had one derivative function. Are antiderivatives unique? No. If you differentiate a constant, you get zero, don't you? So big F is an antiderivative of F, then so is big F plus C, constant C. If G is an antiderivative of F, there is a constant for which big G is equal to big F plus C. In other words, antiderivatives are unique up to a constant. We call this a family. So antiderivative has what's known as a family of solutions. It's nice having a family sometimes. The idea of family of solutions will be important in differential equations. It's also important in physics, by the way. So you study them again. We also use the integral notation, but without the limits, to represent an antiderivative. A lot of texts will refer to the antiderivative as the indefinite integral, and the integral as a definite integral. integral is an integral. And an antiderivative is an antiderivative. But just like with derivatives, where we typically would just say find the derivative to mean find the derivative function, we usually just refer to this as integration when it's actually anti-differentiation. Well, we already have several antiderivatives then. Because remember, an antiderivative is the opposite of a derivative. So here's a list of your basic antiderivatives. We don't see an antiderivative for natural log of x up there. Nor for 4 of the trig functions. There's antiderivative for sine and cosine, but not secant, tangent, cosecant, and cotangent. We will be able to derive antiderivatives for the 4 trig functions by the end of this semester. However, for natural log of x, that requires Calc 2. That requires integration by parts. By the way, the inverse trig functions are also not up there. That also requires integration by parts, which is Calc 2. So for those 7 functions, I'm sorry to say, you're going to have to wait until next semester. I know, it's very upsetting. Very sad. It's a very sad day. That's okay. Can't hog all the fun. There has to be some fun for Calc 2. Properties of the antiderivative. So big F and big G are antiderivatives of F and G respectively. K is any real number. You have your linearity property. So the antiderivative is also linear. So just like we did for derivatives, for the first problem, maybe the second, we'll break it down step by step. But then eventually we're going to shortcut it. All right, so first step, split it across the sum. And then realize, oh, look, I can factor out that 10. I can also technically factor out the 2. But I don't think I need to for the formula. I don't. antiderivative of x squared. This is the power rule for integration. Add 1 to the exponent, divide by that new exponent. That's what it says. What's the power right now? Add 1 to 2, divide. And then plus an arbitrary constant, which is called the constant of integration. What is the antiderivative of a constant? It's the constant times x. Plus a constant of integration. Let's simplify this. What's 10 times a constant? Let's call it C3. What's a constant minus a constant? Call that new constant C. There's your antiderivative. Yeah, I will not be doing that with the constants from now on. This is why you can just wait to the very end to add on a constant, because all of your constants are going to get absorbed into one anyway. Right, so henceforth, I'm probably just going to go term by term, find the antiderivative, add the constant at the very end. Right, just like we do with derivatives minus the adding constant, we just differentiate term by term. Now, what is the most common error with antiderivatives? Yes! You forget the plus C. That's going to happen. I still sometimes forget the C. But I have an excuse because I generally work with a simple antiderivative. Oh, this one's really tough. Is that just T?
T plus C. You forgot C already. I just said that.
See? What did I just say? I can guarantee you that for at least one of you, forgetting those C's is going to be the difference between an A and a B. We'll have to rewrite this one. I'm going to factor out that 1/3 first. How could you rewrite 1 over t squared as a power of t? What is it? Add 1.
Is there a verse quotient
Not directly. But there is a way to deal with fractions. Yeah, it's called partial fraction decomposition. You learn it in Calc 2. So negative 2 plus 1. Divide by negative 1. It's negative 1. Or you may see it written as c minus 1 over 3t. Either one would be acceptable. We'll continue this on Monday. Have a good weekend.